Hello and welcome to Calculus tutorial. We're going to take a look at something called differential equations now. This is sort of a connection to something we did first semester, but we're just going to do it backwards. And so we're going to solve these things called differential equations. Our main strategy for that is called separation of variables, and then our application is proportional growth. So let's take a look at what a differential equation is. This is sort of a throwback to implicit differentiation, taking the derivatives of both sides of an implicit equation. So let's do that real quick to see how these two are going to be connected. So we'll take the derivative with respect to x of the left and the derivative with respect to x of the right. The right side is of course 0. And then we get 2x plus 2y dy over dx. Alright, and then we usually got dx by itself, so subtract the 2x and divide by the 2y. We'll have dy over dx is equal to negative 2x over 2y. And if you want, you can cancel out the 2's. So dy over dx is equal to negative x over y. Now that was first semester, so second semester, hopefully it makes sense that we are going to go backwards. And when you go backwards, you take this equation, which is called a differential equation, mostly because it's an equation with a derivative in it, and we are going to work our way backwards to the original equation, which is going to require us to do the antiderivative. And so whenever you see an equation with a derivative in it, that is technically called a differential equation. Now, how do we go from the bottom back to the top? Well, we have one main strategy for that in this course called separation of variables. That's how we're going to go backwards. So let's take our equation here that we had, negative x over y, and we're going to do exactly what the name says. We're going to separate the variables. We're going to put the y's on this side and the x's on that side. So let's see, to do that, we are going to multiply both sides times y. But then I'm going to do this in one step. We're also going to multiply each side times dx as well. So those y's will go away. We're going to be left with negative x dx on this side. And on this side, the dx's were going to go away. And we're going to be left with y dy. So whatever algebra you have to do to get the y's on one side and the x's on the other. And now we're going to do the opposite of a derivative, which is the antiderivative. And you can see how those dy's and dx's set this up perfectly. So the integral of y dy, 1/2 y squared, plus c, is equal to negative 1/2 x squared, plus c. Now that does not quite look like what we started with, so we have to do a little bit of algebraic manipulation. One nice thing, subtract the c's. Now you might be thinking, hey, c minus c is 0. Not quite. So a number you don't know minus another number you don't know is still a number you don't know. Then let's move the x's and the y's back together. So we're going to add 1/2 x squared to both sides. So we'll have 1/2 x squared plus 1/2 y squared is equal to c. It's looking closer to what we had before. We just have to multiply both sides times 2, and that will cancel out the 1/2s. So you have x squared plus y squared is equal to, and a number you don't know times 2 is still a number you don't know. Which looks very, very similar to what we had at the beginning. We just don't know what c is yet. We would need more information to solve for c, because when you take a derivative, you lose the constant, but then when you take the antiderivative, you get the constant back. But we would need a point to plug in to figure out what exactly that c value is. All right, so that's separation of variables. Let's do a slightly harder example to see just how hard that can get sometimes. So this one's going to be pretty difficult. It's going to take quite a lot of algebra. So first thing though, we need to get the x's and the y's separated. First thing I might recommend doing is write that y prime as a dy over dx. Same thing, still the derivative of y with respect to x. And then I'm going to take this dy dx, add it to this side. I'm going to take the 20x and subtract it to this side. So we'll have 5xy minus 20x now, because that was subtracted over, is equal to dy over dx, because that was added to the other side. Now here we can do some fancy factoring to get the x's away from this y. So they both have an x and a 5 in common, so I'll factor out a 5x, and you're left with y minus 4 is equal to dy over dx. Now I'm going to move the dx over, and we're going to divide by those parentheses. So multiply by dx. But then we're also going to divide by y minus 4. Divide by y minus 4. So that will cross out. We're just left with 5x dx on this side. And on this side, the dx's will cancel out. So we're left with dy over y minus 4, which now sets us up to take the integral of both sides. So the left side is nice and easy. That will be 5 halves x squared plus c. And the other side, so that I'm just going to put the answer, it is natural log of y minus 4 plus c. Now you can hopefully sort of do that u substitution. Is technically I'm making u y minus 4, so then that becomes 1 over u. It's sort of the fancy u substitution it's doing there. You can finish that to make sure that you actually get this, but that's hopefully something you can start doing in your head. And then we want to start trying to get y by itself to sort of plug in these points and solve for c. So the first thing we want to do to solve for c is realize we only need one of these c's, because it will subtract to the other side, and a number you don't know minus a number you don't know is a number you don't know. Now to get y by itself, we are going to do a fancy thing you probably haven't seen since Algebra 2. We are going to take e to the power of both sides. And when you do that, the e and the natural log cancel out, and you're left with y minus 4 is equal to e to the power of all this. Now this gets a little fancy because we have e to the power of 5 halves x squared plus c, and that plus c is in the exponent. Now that looks really bad until you remember, how do exponents add? What happens there? So if I have 5 squared times 5 to the third, that is equal to 5 to the 2 plus 3. The exponents add. And so I'm going to do that backwards. And this is going to be e to the 5 halves x squared times e to the c. All right, because the bases are the same, they're multiplying, you would add the exponents. Well, again, what is e to the power of a number I don't know? It's a number we don't know. So that just simply becomes c times e to the 5 halves x squared is equal to y minus 4. Add 4 to the other side, and we're left with y is equal to c times e to the 5 halves x squared plus 4. All right, and thankfully everything else is pretty darn easy from here actually. Because if we're going to plug in 0 for x and 5 for y, 0 for x cancels out everything up here to be 0. E to the 0 is 1. So we have c plus 4 is equal to 5. So that means c has to equal 1. And so our equation just becomes y is equal to, c is 1, so we don't even really need it, to the 5 halves x squared plus 4. All right, that is just about as hard as it can get. So we're going to take that idea and turn that into a word problem and see what that looks like, because oftentimes that is what you would see on a test, especially the AP test. And so these differential equations come into play with something called proportional growth. So a snake is growing in length proportionally to its current size. This rate can be modeled by the differential equation there, where L is the snake's length in feet and T is years. So we have dl dt is equal to this. Find y equals L at t. So what that means is I need to find an equation for y equals the length with the input of time. If the snake was 1 foot long when it was born. So what that is doing is that is simply giving me the point 0, 1 to plug in eventually. That is the length and that is the time. Time is our input. And so what I simply need to do is find this as a function of L and T. So I'm going to separate the variables. dl dt is equal to 1/3 times 15 minus L. Let's see, so I'm going to divide by this and multiply by the dt. So we'll be left with dl over 15 minus L is equal to 1/3 dt. We're going to take the, don't need the same color, do I? Take the antiderivative of both sides. Let's see, the right side is easy. That will be 1/2 t plus c. And the left side is a little bit more complicated. It's still going to be a natural log of the absolute value of 15 minus L, because it's 1 over, and you would make all of this u. But because the L is negative, when you took the derivative, your derivative would be a negative, and that negative would stay. So I'm going to do that real quick, but if you want to check it, do a u substitution on that to check. That negative is an easy thing to forget. So now that we have all that, let's get L by itself. Although, what is going to happen with this negative? It's a little unclear what happens with the negative, and so right now it might be a good option just to plug in our point. That might give us an easier path. So let's plug that in. X is 0, so that goes away. We're going to be left with c is equal to, if we plug in 1, c will be equal to the negative natural log of 14. I don't need the absolute value anymore because it's not negative on the inside. All right, so let's start there. We have our c value, and we're going to plug in c, okay? I'm going to sort of clean things up a little bit. This is what we have so far. That is the value of c, and this is our equation. Get myself a little bit more room here. So we plug c in. We've got the negative natural log of 15 minus L is equal to 1/3 t minus the natural log of 14. I might get rid of this negative, so multiply by a negative, that becomes negative, that becomes positive. And then we're going to take e to the power of both sides. So e and the natural log cancel out. We're left with 15 minus L is equal to, now because these two exponents are adding, I'm going to rewrite with two bases. So there's the first one times the next one. All right. If we were to simplify this, we would simply add the exponents. But writing it this way shows me that that natural log and the e cancel out. So we're actually just left with, I'm going to put the 14 in front, e to the negative 1/3 t is equal to 15 minus L. And our equation, or our question at the beginning said we need to get L by itself. So to do that, however you want to manipulate this to get L by itself, in my mind, I would add L to this side and then subtract all of this to the other side. So you would have 15 minus all of this, 14e to the negative 1/3 t is equal to L. So now we have our function of L and t, which is what they wanted from the beginning. That's about as hard as it gets, but that's pretty hard. So that is separation of variables for differential equations.